So starting today, we'll be discussing functions. So let us introduce what functions are and some properties and definitions related to functions. So this is section 4.2 in our course module. Okay. So first, let us start with this definition. So let x and y be non-empty sets. Okay, x and y be non-empty sets. A relation or mapping from x to y is a correspondence of elements of x to elements of y. So a relation or mapping from x to y is a correspondence of elements of x to elements of y. So for example, let us consider these two non-empty sets, X. So capital X, it has elements small x sub 1, x sub 2, x sub 3, x sub 4, x sub 5. And then we have capital Y, and the elements of capital Y are y sub 1, y sub 2, y sub 3, y sub 4, and y sub 5. Okay? So as an illustration, say that this red oblong here be the set X, and that X contains these 5 points here. Okay, these 5 elements. And then you have Y, this blue oblong here, and Y contains these 5 blue dots in here. Okay, and then these guys here, so X and then arrow to X1, X1 arrow to Y1, X2 arrow to Y3, take note of that, X3 arrow to Y5, and then X4 arrow to Y2, X5 arrow to Y3, okay? So this is a correspondence between elements of X to elements of Y. This guy here, we read this as X1 maps to Y1. So relation or mapping. So X1 maps to Y1, X2 maps to Y3, etc. Okay? And if we look at this illustration here, we have something like this. So you see your X1 is being mapped to Y1, X2 is being mapped to Y3, X3 is being mapped to Y5, X4 being mapped to Y2, and X5 being mapped to Y3. So this is a relation. And let us name this relation F. Okay, so this is the name of the relation associated to this. And then if we add two more, okay, so we have the original relation earlier. And then let's say your X2 also maps to Y1 and your X5 also maps to Y4. So earlier you had X2 maps to Y3. So your X2 is being mapped to Y3. And then with this additional mapping here, your X2 is also being mapped to Y1. And we also map X5 to Y4. So originally, your X5 is being mapped to Y3, but we add this mapping here, X5 is being mapped to Y4. So again, this is a relation. And let us name this relation G. Okay? Let us name this relation G. Let's have another example here. This time, let capital X be the set containing the numbers 1, 2, 3, and 4, and Y be the numbers containing 1, 2, until 12. Okay? So 1, 2, 3, until 12. So this is your X here, and this is your Y here. So your X contains 4 numbers, 1, 2, 3, 4. But in this relation, we are just defining 1 being mapped to 1 and your 3 being mapped to 3. So you have this point here being mapped to 1 and then this point here being mapped to 3. Okay? And your 2 and 4 from x, they are not being mapped to anybody. Okay? And then, of course, there are other points in the set y where in which they don't also have partners from x. Okay? So 1 is being mapped to 1, 3 is being mapped to 3. And let us label this relation H. Okay? So this is another example of a relation. And then let's have this relation. So still we have your capital X set containing the numbers 1, 2, 3, and 4, and Y, the set containing numbers 1, 2, 3 until 12. Okay? And look at this. We name the relation I, okay? And then we write this relation as follows. You have I, and then there's colon, and then capital X, and then you have the right arrow, capital Y. So this means that the set X is being mapped to the set Y. Okay? And then below this, we have this X. So if you get an element X from capital X, that element X is being mapped to the 3X from the capital Y. Okay? So this X here is being mapped to 3X. So suppose we get X equals 1, then that number 1 from capital X is being mapped to 3 times 1. And 3 times 1, that's equal to 3. So your 1 is being mapped to 3. If your X is equal to 2, then this 2 will be mapped to 3 times 2, which is 6. You get X equals 3, then this 3 will be mapped to 3 times 3, which is 9. And if your X is equal to 4, this 4 will be mapped to 3 times 4, which is 12. Okay? So this guy here is the enumeration of this mapping. So this X maps to 3X. This is the rule that you want to satisfy. And this guy here, you just enumerated all of them. So there's only a finite number of elements from X. So you can enumerate all of these mapping here following this rule. And as an illustration, your 1 here is being mapped to 3, your 2 is being mapped to 6, 3 is being mapped to 9, 4 is being mapped to 12. Okay? And again, we label this relation I. And if we want, we can rewrite this mapping, okay, in table form or tabular form. So in here, we write in the first row, we have the values of X. So this will be coming from the set X. And then on the second row, we have the corresponding values for Y. So it's coming from the set capital Y. So you have in the first row here, you have 1, 2, 3, 4. And then on the second row, corresponding to 1, that's 3. Corresponding to 2, that's 6. Corresponding to 3, that's 9. And corresponding to 4, that's 12. Okay? So for this particular example, we now have several ways to write a relation. So you have an illustration, okay? You have the rule in here. You have the rule in here for that mapping I. You also have this enumeration. You enumerate each element of X when it will be or where, which is its partner from the set Y. So you can enumerate that. So your 1 is being mapped to 3, etc. Or in tabular form. So this one here, it's like this guy here. It's also an enumeration, but it's written in tabular form. Okay? So these are some ways to write your relation. Okay? Questions so far? Okay, so let us define now what a function is. Okay, so let x and y be non-empty sets. A function take note of this, a function from x to y is a correspondence of every element of x to a unique element of y. Okay? There are two things to take note. So we are defining a function here. Okay? And the correspondence is that every element of x is related or corresponds to a unique element of y. So each element of x is mapped to a unique element of y. Unlike in the relation, okay, unlike in the definition of relation, it only says correspondence of elements of x to elements of y. Okay? Correspondence of elements of x to elements of y. But in function, okay, we want every element of x to correspond to a unique element of y. Okay? So for example, let us recall the relation f with this um, mapping. Okay? So notice your x1 is being mapped to y1 and your x1 is only mapped to y1. Your x2 is only mapped to y3. Your x3 is only mapped to y5. Your x4 is only mapped to y2. And your x5 is only mapped to y3. Okay? So correspondence of every element of x. So from x1 until x5, each element of the set x corresponds to a unique element of y. So your x1 is uniquely mapped to y1. Your x2 is uniquely mapped to y3. Okay? x3 is uniquely mapped to y5. x4 is uniquely mapped to y2. x5 is uniquely mapped to y3. Okay? So this relation f is actually a function from x to y. So every element of the set x is mapped uniquely to an element of y. Okay? Question. If you look at this, notice that y3 has two partners. y3 is being partnered to x2 and y3 is being partnered to x5 also. But this guy here doesn't violate any of the conditions here. Okay? Our condition is that all the elements of x must have a partner. Okay? And all and each element of x must only have one partner. Okay? It did not tell us that the element of y must have only one partner. We don't care about y in here. Okay? So we only care about x to define a function. Okay? So this guy here is a function from x to y. Now, let us recall the relation g. So this time we added, so it's just the function f and then we added these two conditions. x2 going to, x2 is being mapped to y1 and x5 being mapped to y4. So particularly this x2 is now mapped to y3 and y1. Okay? And also your x5 is being mapped to y3 and y4. Okay? Now, the first condition here is that every element of x must have a partner in y. So you have your x1, x2, x3, x4, x5. They have partners in y. Okay? But the other condition is that their partner must be a unique element of y, meaning they are only partnered to a single y. So this x2 here is partnered to y1 and y3. And also your x5 here is partnered to y3 and y4. So this x2 and x5, okay, violate the uniqueness part. Although they have partners, okay, but it's not unique, or their partners are not unique. Okay? Your x2 has two partners, y1 and y3. Your x5 has two partners, y3 and y5. So this means that your relation G is not a function from x to y. Okay? So it's not a function from x to y. It is a relation, but it is not a function. Okay? Let's look at this next example here. So you have your capital X, the set containing 1, 2, 3, and 4. Capital Y is the set containing 1, 2, 3 until 12. Okay? And then we recall H, the relation H. Okay? Now, notice 1 has a partner, 3 has a partner, but 2 and 4, they are both elements of X also, but they don't have corresponding partners. Okay? So it violates this part here. Every element of X must correspond to a unique element of Y. But in here, there are two elements from X which do not correspond to anything. And therefore, because of that, this H here is not a function. Okay? Question so far? For our next example here, let us recall the relation I. So the relation I, you have X element from capital X. It should be mapped to 3 times X. Okay? So your 1 has a partner, it's 3. Your 2 is mapped to 6. Your 3 is mapped to 9. And your 4 is mapped to 12. So each element of X has at least one partner. In fact, each element of X has a unique partner. Okay? The unique partner of 1, it's just 3. The unique partner of 2, it's just 6. The unique partner of 3 here, it's just 9. And the unique partner of 4, it's just 12. Therefore, this relation I is actually a function. Okay? So it satisfies both conditions. Each element of the set X must be mapped to a unique element in the set Y. Okay? Question? So, let us formalize the definition. So, let X and Y be non-empty sets. A function from X to Y, okay? And we write the function, say, if we name the function F, okay? We write F colon X, right arrow Y, okay? So this is a relation that associates with each element of X to exactly one element of Y. Okay? So a function is a relation that associates with each element of your X here to exactly one element of Y. Okay? So let F colon X right arrow Y be a function. Okay? Let F be a function. The set X, this guy here, okay, we call it the domain of F. And we denote it by this, dom F. So the domain of F. Okay? The set Y, so this guy here, okay, we call it the codomain of F. So take note of the name, codomain of F. Okay? So this guy here, it's the domain of F. This guy here, it's the codomain of F. Now, if F associates the element X from capital X to an element Y in Y, we say that Y is the value, okay? We say that Y is the value or image of F at X, okay? Now, if we collect all the images of F, then we call the collection the range of F. Okay? Range of F. And we denote that by run F. Okay? So again, this guy here, it's the domain. X, capital X here, it's the domain. Capital Y here, it's the codomain. Now, if you have an element X and it has a partner in Y, it should have because we are talking about a function. Okay? So if we collect, if that partner in Y is called the value or the image of F at that particular X. Okay? And then if we collect all the images of F, okay, we call that set the range of F. So do not be confused with this set here. It's called the codomain. The range of F, okay, it's the collection of all values or images of F at X. Okay? So for example, this was a function and I told you that these guys here, they have unique partners. Okay? They have unique partners from Y. Now, your X1 is associated to Y1. So Y1 is the image of F at X1. Okay? So let me just write that. So in here, Y1 is the image of F at X1. Okay? Here you have X2 is being mapped to Y3. So in here, we say Y3 is the image of F at X2. And you can write Y5, it's the image of F at X3. Y2 is the image of F at X4. And Y3 is the image of F at X5. And we said F is a function from X to Y. We already mentioned that. But in here, the range of F, take note of this. Notice only Y1, Y2, Y3, and Y5, okay, have partners from X. So the range of F, it's just Y1, Y2, Y3, and Y5. Y4 here, it's not included in the range of F. Okay? So, codomain of the function F, it's all of them Y1, Y2, Y3, Y4, and Y5. That's your codomain. But if we only talk about the range, we only get those Y's. Okay, those Y's which have partners from X. Y4 does not have any partner from X. It's not part of your range. Okay? Is
I have
that
question.
clear? Sure.
How about Y3 who has domain, two domain? It's not function, yeah?
Where is to what do you mean?
Y,
Y3?
Y3.
No, your Y3, we don't care about how many partners your Ys have. We only care about the partners of X. Partners of X must be unique. We don't care about the partners of Y. Y,
So
particularly your Y3, you said, it has two partners, X2 and X5. And we don't care. It is still a function. Okay? So, every element of the set X has a unique, okay, has a unique partner in the set Y. X2, it only has one partner, Y3. X5, it only has one partner, Y3. That's totally fine
okay.
for X2 and
Mhm.
X3, X5. Your Y3,
So
it has two partners, and we don't care about that. Okay?
so X supposed to be just one partner.
Yes, X must have
Okay.
only one partner. Your Y,
Okay, thank
don't
you.
care. Yeah, that's a very good question and observation. Okay? So, every element, every element of X must only have one partner. In Y or from Y, the elements may have two or more partners. It may have no partner, just like your Y3 has two partners from X, X2 and X5. Y4 doesn't have any partner. We don't care. It's still a function. Okay? That's a very good question. So again, in here, you have your range Y1, Y2, Y3, and Y5 because Y4 does not have any partner from X. Okay? Let's look at this. We mentioned that I is a function. So look, 1, 2, 3, 4, they have a unique partner. Each of them has a unique partner. Okay? 1 is partnered to 3 with 3, 2 with 6, 3 with 9, 4 with 12. Set Y contains all the numbers or all the integers from 1, 2 until 12. Okay? So this is your codomain. But if we only look at the range of I, the range of I contains only 6 or 3, 6, 9, and 12. 3, 6, 9, and 12 because these are the only numbers from Y that have corresponding partners. Okay? So is the definition of range clear? Any question? Now, let's look at this. Some remarks regarding function. So earlier I said let f colon x right arrow y be a function. We simplify this to the following. Let f be a function. Okay? Let f be a function. So it is possible that you will see the capital X or the capital Y, but we will just simply say let f be a function. There are also some cases where you don't see this capital X, capital Y. Okay? Now, all functions are relations because these functions are correspondence between two non-empty sets. Okay? But there are relations which are not functions. Just like your relation G. We said it's not a function, okay? Because it violates some of the conditions. Okay? Where is that? In here. Okay? G is not a function. We said this is a relation, but this is not a function. So there are some relations which are not functions. Okay? Now, we can have an alternative definition of function. So, a function from x to y, this is a subset of this, x cross y. This is read as x cross y. Okay? And the definition is the same. For every x from capital X, there is a unique y from capital Y such that, look at this, an ordered pair x comma y, element of f. Okay? So x comma y, element of f. Okay? So remember, I have already shown you this kind of notation. So we can also use this notation in terms of functions. So in here, this set here, x cross y, it's the collection of all ordered pairs, x comma y. This small x must be coming from your capital X. The second here, y, should come from your capital Y. So this is an ordered pair. Okay? So what does this mean? If your function is written this way, okay, this set here, ordered pairs x comma y, where x is coming from capital X and y is coming from capital Y, this set here defines a function, take note of that, if no two ordered pairs have the same x coordinates. So if you listed all ordered pairs, okay, if you listed all ordered pairs and you don't see any two ordered pairs which have the same x coordinates, or this guy here, the first guy here, then the set that you have is a function. Okay? Let us consider this. We have the function small f from before. We said that this is a function. We write now that function in terms of this. So your x1 has a partner y1. Your x2 has a partner y3. Your x3 has a partner y5. x4 partner is y2. x5 partner is y3. Okay? So you can write the function in terms of this. Okay? Let's look at the function I. Let's look at the function I. Your 1 has a partner which is equal to 3. The 2, its partner is 6. 3 is partnered with 9. 4 is partnered with 12. Okay, so you can write the function in this form. And notice there are no two pairs which have the same first x coordinate, first coordinate or x coordinate. So this pair here, x coordinate is 1. This pair here, it's 2. Here 3, here 4. Similarly here, x1, x2, x3, x4, x5. And there is no another pair which has either of these 5 is the x coordinate. Okay? If you recall, let me write it here. If you recall g, if you recall the function g, you have your x1, y1, okay, x2, y3, and then blah, just try to write the other. And then you also have another x2, and the partner is y1, if I remember it correctly. Okay, so this guy here, this is another ordered pair. Okay, but the x coordinate, which is x2, okay, x2 and x2 here, they have the same. They are the same, I mean. So we have two ordered pairs which have the same x coordinate. Okay, so again, not a function. If we base our definition using the alternative definition that was stated earlier. So in here, okay, defines a function if no two ordered pairs have the same x coordinates. So this function, this guy here, this relation is not a function. You have x2 here and you have also x2 here. Okay? Question. Let's look at this example. Say, let us consider the set X. And the set X is the set of ordered pairs X comma Y, which satisfies, or X and Y satisfy, X squared plus Y squared equals 1. Okay? So, this set here does not define a function. Okay? So, you collect all those pairs, X comma Y, such that X and Y satisfy this condition here. X squared plus Y squared must be equal to 1. And this is not a function because, for instance, if you take your X equals 0, then possible Y's are 1 and negative 1. Positive 1 squared, that's equal to 1. X equals 0, correct? So this is gone. So you only have Y squared equals 1, and possible values for Y are 1 and negative 1. So you have two ordered pairs. You have two ordered pairs which have the same X coordinate. 0 partnered with 1, and 0 is also partnered with negative 1. So this is not a function. Okay? Question? Let's have next remarks here. Let f be a function. Let f be a function. Now, if y is the image of f at x, okay, if y is the image of f at x, we write y equals f open parenthesis x close parenthesis. And this is read as y equals f of x. Okay? So this is read as y equals f of x. Okay? So meaning the value of f at x, that's equal to y. Or y equals f of x. Okay? Now, we also say f of x is the value of f at x. Remember, y is the image or the value of f at x. If we write y equals f of x, this means f of x is the value of f at x. Okay? We call x the independent variable. Okay? Because this x here does not depend on anything. That's why it's called independent variable. Your y is called dependent variable. Dependent because you choose your x, whatever x you want, and you evaluate. I'll introduce the word evaluate. Okay, you evaluate that at in f, you will get a value for y. So y depends on the value of x you chose. So y is called dependent variable. Okay? Now, in this course, we assume R, okay, this guy here, to be the codomain of our functions. Okay? So, this symbol here, okay, this is the set of real numbers. The set of real numbers. Okay? Sometimes we write this Sometimes we write this as, so you have your R. This is the set, open parenthesis, from negative infinity to plus infinity. So we collect all possible numbers, whether integer, rational, or irrational. We collect all of them. Okay? So the function capital F, or the function small f, has codomain, okay, the set of real numbers. So this y here will always be the set of real numbers. And we say that our function is real valued because we only consider real numbers. Okay, so in this course, we only consider real valued functions. But take note, the range of your function, it is possible that it is not the set R. It is possible that it's not from negative infinity to positive infinity. Okay? Take note that there's a possibility where a certain number is not an image of any element of the domain. Okay? Now, if the domain is not given, take note of this. If the domain is not given, take it to be the largest subset of R, such that if x is in that subset, f of x is a real number. Okay? So we compute. If your capital X is not given, we compute for that capital X. And the condition is, if you get some number, okay, if you get some number and you have f of x to be a real number, meaning you get a number x, you evaluate it in f, and you get a real number, then that x here must be in this capital X. Okay? And we collect all those x's. Okay? And that will become our domain. We call this the natural or implied domain of F. Natural or implied. We don't write it like this. A lot of times we'll just write the function like this without this x right arrow. So let f be a function. We solve for the domain. We solve for this capital X using this condition. So we call it the natural or implied domain of F. Okay? So we'll have several examples on finding the domain. That's one of the goals in this section. We will be asked to find the domain of your function. Okay? Now, if f is not defined at some value x, okay, if f is not defined at some value x, then we say x is not in the domain of f. So this symbol here, it means not in or not inside. Okay? So if f is not defined at x, meaning we don't see, when we try to evaluate this x at f, we don't get a real number. So it means that x is not in the domain of f. And we also say f of x does not exist. Okay? So again, to make these things clear here, we will have examples. So it will be better understood. I mean, they will be better understood if we consider some examples. Let's start with this one. Find the natural domain. Here, your function is f of x equals x plus 1. So when you get a real number x, you add 1, that will be the image of your x. So in here, I have written domain of f equals the set of real numbers. Or let's write this as from negative infinity to plus infinity. Okay? Because you get any real number, add 1, you'll again get another real number. If you get x equals 1 half plus 1, that's just 3 halves. It's a real number. If you get square root of 2 as your x, you add 1, 1 plus the square root of 2, that's another real number, etc. So whatever real number you get, you evaluate it in f, and then you will still get a real number. Which means the domain of this function f, it's the set of real numbers. There are no restrictions, in short. Okay? Let's have this. G of x equals x plus 1 over x minus 2. Okay? Take note of this. If x is equal to 2, the denominator will be 0. Correct? If x is equal to 2, the denominator will be 0. And therefore, you will have something 2 plus 1, that's 3. 3 over 0. And that's not defined. Okay? So, g is not defined at 2. Okay? Which means that this 2 here, it must not be inside the domain of G. Correct? Now, if you get any other real numbers, okay, say x equals 1, you will have what? On the denominator, you have 1 minus 2, that's negative 1. It's fine. Numerator, you have 1 plus 1, that's 2 over negative 1. It's a real number. If you get x equals negative 1, your denominator, it will be negative 1 minus 2. That's negative 3. That's your denominator. It's totally fine. Your numerator, it's negative 1 plus 1. That's 0. So 0 over negative 3, it's just 0. It's a number. So if you get any other real numbers, except for 2, okay, except for 2, the function g will be defined. Okay? So if you get any real number, except for 2, the function g will be defined, or the relation g will be defined. Okay? Which means the domain of g, it's the set of real numbers except. So this is a backslash. Okay? This is a backslash. So the set of real number except the set containing 2. Okay? So let me rewrite this again. So you have the set of real number except. So this is a backslash. So I'll emphasize that backslash. The set containing 2. So this means we are removing this element 2. Okay? And this guy here may also be written in the following manner. So this is the set from negative infinity to plus infinity except the set containing 2. Remember, your R, it's just this guy. So we just copied. Okay? This can also be written in the following manner. You have open from negative infinity, comma, to close parenthesis, and then this symbol here. So this symbol here, and then open parenthesis, to plus infinity. Okay? So this guy here or this guy here can also be written using this. I'm not sure if I already mentioned this symbol, but this symbol here, this means union. You combine the two. Remember this set here? Okay? If you wrote this graphically, so this symbol here, if you wrote this graphically, you will have something like this. So this is your 2 here, and then you open this, and then that's towards this direction. I mean, to the left. And then for this guy, if you wrote this graphically, this is your 2, okay? This is your 2, and then you use this, and then this is the graphical representation. So this guy here is represented by this graph. This guy here is represented by this graph. Okay? You get the union. You get the union. This guy here is the union. If you get the union, this is how we're going to draw it. So you have this, okay? And this is your 2 here. This is your 2. We combine this into the following. You put a circle inside that. Okay, you put this circle on that spot. The 2. Open. Okay, not shaded. And then just draw this ray going to that direction and this ray going to this direction. So this graph here means that you collect all real numbers except this whole. So we'll think of this as a whole. There's nothing in it. You'll just what? Go into that and you will not get anything. So it's a whole. So when you write this 2 below that, it means the 2 is not included. Okay? So again, the domain of G, it's the set of real numbers except 2. So R backslash braces 2. Okay? So this guy means 2 is not included. Or you can write this in interval notation. It's negative infinity to plus infinity backslash the set containing 2, meaning you are removing 2. Or in this notation, you have negative infinity, comma 2, then close parenthesis, union, open parenthesis 2, comma infinity, then close parenthesis here. So this guy here means we are not including 2. This guy here, because again, the reason is we are using parentheses here. Also, we are using parentheses here. So this means that 2 is not included. Okay? And graphically, it's drawn this way. Okay? Question. Now, some students do this. They use this notation, but they write it this way. Okay? Mathematically, this is incorrect in a sense that this guy here is not the same as this. Okay? Mathematically. But a lot of students do this. I'm not sure why they are used to doing this. Okay? But I do not recommend, and I am not teaching you to write this if you mean this. Okay? If you mean this. Okay? So if you're someone who do this, stop doing it because mathematically it's not the same as this. This one, um, take take note that when you write this, you are trying to remove a set of elements. This is a set, you remove some set. Okay? In here, uh, you have a set, you remove a number. But you must operate on set with set. Okay? So that's an abstract explanation. So again, if you mean something like this, if you mean you want to remove some numbers from a set of elements, you must put the numbers inside a set also, just like this guy. Okay? So do not use this. Okay? So not, please do not use. Okay? Please do not use. If you meant, or if you mean set of real numbers except the set containing 2. Okay? Question? Another function here, h of x equals square root of x squared minus 9. Try to check that this is a function. Okay? Now, we said that if you have a square root, the one inside must be positive or equal to 0. So if we want to solve for the domain of h, okay, if we want to solve for the domain of h, we require x squared minus 9 to be greater than or equal to 0. Okay? We require x squared minus 9 to be greater than or equal to 0. So try to solve this inequality. I already showed you how to do this with x squared minus 1 greater than or equal to 0. You do the same. You do a very similar solution. You factor x squared minus 9, and then you will have something like x minus 3x plus 3. So x minus 3 times x plus 3 must be greater than or equal to 0. So both must be positive or both must be negative. Okay? So try to work on this inequality. Okay? And then you will see that if you work on this inequality, what you will get is that your x must be less than or equal to negative 3, or your x must be greater than or equal to positive 3. This is the one that you will get. Okay? This or here in symbol, it is your union. That's why you have this union here. Okay? That or means union. So you combine. You combine this set with this set. And this set, take note, this set, it's your negative infinity, comma, negative 3. And since we also want equality, you will get this. And then union. And then for this set, you have your 3 to plus infinity. And we also want equality, so you have square bracket here. And that's what you will get in here. So this is the natural domain. Take note, 0 is not included in here. Because if you take x equals 0, this becomes 0 minus 9. And therefore, you will have square root of negative 9. And that's not defined, at least in our course. So you cannot have that 0. And therefore, 0 is not in the domain of this function. Okay? Question?
I have a question.
Sure.
The x greater than 3, why its signs change?
What do you mean why signs change? If you try, okay, so I think this is what you want to see. If you try, because you have here, right? You have factors x minus 3, x plus 3.
Mm-hmm.
And this must be greater than or equal to 0.
Okay.
So you divide this into two parts. Either you have x minus 3 greater than or equal to 0 and x plus 3 greater than or equal to 0. And then the other guy here, you have x minus 3 less than or equal to 0 and again, that's your end, x plus 3 less than or equal to 0. They must have the same signs. X minus 3 must be greater than or equal. X minus 3 must be positive. X plus 3 must also be positive. So if you multiply them, you will get positive. Or x minus 3 must be negative and x plus 3 must be negative. So negative times negative, you'll get positive. Are we good at this part?
Yeah, okay. Thank you.
So from here, so this is almost the complete solution. From here, what you will get is your x must be greater than or equal to 3 and your x greater than or equal to negative 3. So you combine this and meaning both must be satisfied. And then for this, you will get x less than or equal to 3 and x less than or equal to negative 3. So you will see this. You will be able to solve this. So this guy here tells you your x must be greater than 3, while this guy here, it will tell you that your x must be less than or equal to negative 3. That's why you have these two guys. So they changed signs. It's like you changed the sign. Okay? Other questions? For our next function here, k of x equals x squared minus 1 over x minus 1. Look at this. The denominator, it's x minus 1. If x equals 1, the denominator is 0, which means we cannot do this. You cannot have a denominator 0, whatever your numerator is. Okay? Which means we remove 1. Okay? We remove 1 in the set of possible domain. And then whatever other numbers you use, okay, whatever number you get, except for 1, of course, this will have a value because the denominator will not be 0. So this tells us the domain of K, it's the set of real numbers except the set containing 1. Okay? question. Question. Now, let's have the following. Let us consider p of x equals 3x squared minus 5x. So this is a function. Okay, this is a function. And notice you have a quadratic expression on the right-hand side. And you can take any x. You take any x, you evaluate or you plug in your x here, and then you will get a real number. Correct? You will get a real number. So whatever your x is, you plug it in here, you will still get a real number. So let me write it here. The domain of P, this is the set of real numbers. Okay? Now, let's look at this. Suppose we take C, any number C. Okay? And then let's just take 1 also. And then we evaluate P of C plus P of 1. So meaning, for the P of C, we just replace the x's here with C. And then for the P of 1, we just replace the x's here with 1. And then you add them. Okay? So you have here, your x is replaced by C. So you will have your 3c squared minus 5c. So you replace your x with C. And then plus, this is the plus here. So for emphasis, I will write that. So this is your plus here. That's this guy here. This guy here, it's your P of C. And then P of 1, so we replace your x with 1. So it's just 3 times 1 squared minus 5 times 1. So this guy here, it's your P of 1. Following so far? So, if we add them, this is what we'll get. We just need to simplify. 3 times 1 squared, that's just 3, minus 5 times 1, that's just 5. So 3 minus 5, that's minus 2. So you will get 3c squared minus 5c minus 2. Okay? This time, let's have P of c plus 1. So you get a c, add 1. So please, P c plus 1. And then you have that c plus 1, you evaluate that in P. So you have P of c plus 1. Meaning, the x is replaced by c plus 1. So this x here, we will replace it with c plus 1. And this is what we will get. 3x squared, that becomes 3 times c plus 1 squared. Minus here, 5x. So 5 times c plus 1. Okay? And then let's see, we expand this. We expand c plus 1 squared. We distribute this 5 into this c plus 1, and then we simplify. So expanding, you will have c squared plus 2c plus 1 if you expanded this. Then here we distribute, this becomes minus 5c minus 5. And then this guy here, we distribute. And then let us simplify. So in here, if we distributed this, you will get c squared, 3c squared plus 3 times 2c, that's 6c plus 3. Okay? And then we simplify, you have 6c plus minus 5c, that's plus c. And here you have 3 minus 5, that's minus 2. But what's the point? P of c plus 1, you get 3c squared plus c minus 2. On the other hand, you have P of c plus P of 1. This is 3c squared minus 5c minus 2. This guy and this guy are not the same. Okay? The point is, if you have a function, f of a plus b, it's not always the same as f of a plus f of b. So don't just distribute your function. Remember this, square root of a plus b. This is not the same as square root of a plus square root of b. Or you have your a plus b squared. This is not equal to a squared plus b squared. Okay? You have this or you have this in more generality, or in more generality, or in general. If you have a function, it's not always f of a plus b not equal to, a given function f of a plus b is not always equal to f of a plus f of b. So this square root here, it's an example of f. This square here, it's an example of f. So we now generalize it. Okay? So don't just distribute. Okay? Let us consider again that function p. Okay? So this time, you have p of x plus h minus p of x over h. So in here, we evaluate the function p at x plus h. In here, we just copy p of x. And then we divide everything by h. So for the first part here, you replace your x with x plus h. So you will get 3 times x plus h squared minus 5x plus h. So this guy here. So this guy here. This is this. Okay. And then you have the minus. So that's your minus. And then you have p of x. So you just copy your p of x. You have your 3x squared minus 5x. So this guy here, this is this. And then of course you have over h. Okay. Then let's simplify. You expand this, you distribute this, you distribute the minus. Okay. And you will get something like this. So you expanded x plus h squared. So x squared plus 2hx plus h squared. So practice on your expansion if you don't get this immediately. Well, I know some of you, okay, who still do something like this. So this guy here, they still write x squared plus h squared. And again and again and again. This is not correct. You won't get any point if you do this. So please try to practice your binomial expansion. So we have expanded x plus h squared. And then in here, you distribute your 5. So you will have minus, so there's negative there, so minus 5. So minus 5x here. So minus 5 times h, that's minus 5h. And then here you distribute your minus. So minus 3x squared minus minus, that becomes plus. Correct? And then let us simplify. You expanded this. Let us try to distribute now. You will have, so for this part here, you will have 3x squared plus 6hx plus 3h squared. So notice, you have 3x squared here and then minus 3x squared here. So this guy here will cancel this guy here. Okay? And then notice this, you have minus 5x, then plus 5x. So this guy here will cancel this guy here. So the simplified version will be this guy here, 6hx plus 3h squared, then minus 5h. And of course, you still have your denominator h here. And then notice this has h, this has h, this has h. You can factor that h, okay? And then you cancel the h in the denominator. So what happened here? This guy here equals h times 6x plus 3h minus 5. And then you divide this by h. So this h here will cancel the h here. And you will be left with 6x plus 3h minus 5. 6x plus 3h minus 5. Okay? Question. So, I presented this because this expression here has a special name. Let f be a function. The difference quotient of f at x, okay, is this expression. So similar to this expression. Okay? So you have f of x plus h minus f of x all over h. Of course, your h here, it's not equal to 0. So the difference quotient. Okay? And this is a very special expression because if you're going to continue studying calculus, okay, you will see this a lot of times. Okay? You will see this a lot of times in your calculus. Calculus 1 possibly. Actually, yeah, in calculus 1. Okay? So, any questions so far?
No, thank you.